This is Lab 3 Circuits. So the purpose of this lab was to investigate how resistors and capacitors affect a circuit, measure a circuit's potential difference to show the loop rule, and show that charge in a capacitor grows or decays exponentially. And the result of this lab was that in a system with a 3-volt battery, the 47 ohm resistor had a potential drop of 0.9 volts, and the 100 ohm resistor had a potential drop of 2.0 volts. And when charging and discharging a capacitor with a 4.5 ohm light bulb, it took around a minute, while a 1 ohm bulb took around 10 seconds. The first concept in this lab is Ohm's law, which is very simple. It's just that the change in voltage is equal to current times resistance. And the loop rule, the second concept, is that around any loop of a circuit, the sum of the potential differences must equal 0. The third concept is the node rule, which is the current going into one part of the circuit must be equal to the current going out of that part of the circuit. So if you have one wire going in, 2 wires going out, the current must be equal between those. The next concept is the concept of series versus parallel. So for resistors in series, their resistances will combine together, so you have R1 plus R2 plus R3 and so on. But for resistors in parallel, their resistances will combine inversely, so it'll be 1 over R1 plus 1 over R2 plus 1 over R3 and so on. And for capacitors, all you have to know is that when they charge or discharge, they do so exponentially. So before we get into the procedure, it must be noted that we used real circuit components for this lab and that the system is the circuit and everything else is surrounding. So for the first part, we first created a circuit with a 3-volt battery, 47 ohm resistor, 100 ohm resistor, and 2 multimeters. And then we set both multimeters to read amps, and we observed the current, and then we reversed the connection of one of them and saw what would happen. Then we changed one of the multimeters to voltage and found the data. Then measured and created a graph of the potential differences throughout the circuit. And we connected a voltmeter across the 100 ohm resistor and saw what happened. Then we did so with an ammeter and saw what happened. And then we calculated the resistance of different elements throughout the circuit. For the RC circuit, we created a circuit with a 3-volt battery, 4.5 ohm light bulb, and capacitor. And once we created it, we timed how long it would take to charge the capacitor or how long it would take the bulb to die. Then we connected the capacitor directly to the light bulb and saw how long it would take the capacitor to discharge. And then we repeated this process with a 1 ohm light bulb instead. So for the results, in the circuit with 2 ammeters, the prediction would be that both would read 20.4 milliamps based on Ohm's law, as the voltage is 3 and the resistance is 147 when combined because they're in series. So the current would be 20.4 milliamps. But in reality, the first one was 18.7 milliamps and the second one was 19.0 milliamps. And when the connection was reversed, the sign of the current turns negative. And once we switched one of the multimeters to voltage, we read that the voltage was 3.1 volts, which makes sense. It's around the battery. And the current was 21.8 milliamps, which is around the predicted value. And for the potential differences, the first resistor, 47 ohms, had a 0.9 voltage drop, and the 100 ohm resistor had a 2.0 voltage drop. And when you find all the potential differences and graph them, you'll notice the loop rule shows and it basically goes down to 0. But it's basically 0.1 volts, and that could be because of rounding error by the multimeter, or the battery wasn't fully 3 volts, or the wires had some resistance that we didn't account for. And some of the extra questions for this part was, when you add the voltmeter, the circuit changes, but the current does not because current comes through a circuit. And when you connect the voltmeter across the 100 ohm resistor, the current does not change because the voltmeter's resistance is so large that it has almost no effect on the circuit, and it keeps most of the current still flows through the 100 ohm resistor. But when you replace it with an ammeter has very little resistance, so most of the current starts flowing through the ammeter, so basically makes the 100 ohm resistor negligible. Basically, there's only one resistor, 47 ohms, which would raise the current. And when we calculate resistance, the 47 ohm resistor have a 47 ohm resistance, 100 ohms would have 100 ohm resistance, the wires kind of had 0 ohms, and the ammeter was 5.3 ohms. For the capacitor, we found that with the 4.5 ohm bulb, charging took about a minute, 47 milliseconds, discharging took around the same time, a minute. The 1 ohm bulb took around 11 seconds to charge and 10 seconds to discharge, which makes sense because then it would show that charging and discharging is exponential. And some sources of error could have been that the battery may not be a full 3 volts, the wires have some resistance, there could have been rounding errors, or the hand timing was not completely accurate for the last part. And for the discussion question, An ideal model would predict the capacitor to reach full charge almost instantly because there is no resistance, but this is obviously not possible. In real life, for us, it took about 4 seconds, and this could be because of resistance in the wire or within the capacitor itself would increase the time to charge. So, in conclusion, by Ohm's law, more resistance means less current will flow through the resistor, potential difference throughout a circuit will equal zero, and capacitors charge and discharge exponentially.